Hi, my name is Crystal and I'm team leader of Group 5 for the Mars Rover project, and these are my teammates.
Hi, my name is Michael.
Hey, I'm Orla and I'm part of my
Edward.
Hi, my name is Akshanth. The problem definition phase is the first step in CliveTheme's 5-step engineering design process, as it provides the foundation for the final solution to a client's problem by formulating a problem statement. The problem statement frames the requirements of a project by outlining the objectives, constraints, functions, and attributes of the solution. Consequently, it's a powerful tool which identifies the goals and scope of the design process. But one may ask, what really makes the problem statement so important? As CliveTheme details in Chapter 3 of Engineering Design, a project-based introduction, the revision of a problem definition into a statement will reflect a fuller understanding of the design problem. This is echoed by Sacred Heart University's belief that it helps form a common idea of the objective, identifies key terms, and puts forth viable approaches to solving said problem. Additionally, a strong problem statement focuses on the engineering parameters which define the inherent conflict of the problem. The use of engineering parameters intertwines with G.S. Atchuller's 1940 Theory of Inventive Problem Solving, or TRIZ. He defines the 39 standard technical characteristics that are prevalent in most engineering problems, such as durability and stability. TRIZ gives the basis of a practical methodology which is incredibly applicable to problem formulations, systems analysis, and failure analysis, aspects which are significant in the design processes. Thus, the inclusion of these key parameters in the problem statement makes it imperative to the engineering design process and the overall success of the project. Furthermore, the problem statement will be the backbone of the team charter, essentially an agreement between the team and the client regarding the project's objectives. Hence, it is an effective communication tool if a client may have limited technical knowledge about the problem, by defining concisely to all parties involved the intentions of the project with no ambiguity, as Dr. Yunlock Lee stated in 2021. The problem statement further gives ample opportunity to the client for collaboration with the team to highlight any desired or undesirable aspects or raise any additional constraints concerning the project, which can then be adopted into a revised final problem statement. Thus, the problem statement is especially important in the problem definition phase due to its overwhelming impact on the engineering design process.
In order to communicate a comprehensive problem statement, we decided to focus on 4 main points: context, objectives, constraints, and attributes. Let's take a look at each individual part. Providing context means we'll be able to frame the design problem in such a way to think about the best possible solutions. In this case, the focus is on Mars. So then the team and client will understand what simulation environment the vehicle will actually be operating in. For objectives, the highlighting in blue shows how the main focus is on what the vehicle must be able to do. We identified this earlier in the objective tree to see which function was the most important. There is also an emphasis on the simulation part of the problem to ensure that there is no bias or ambiguity. This is to clearly express that the team is not actually building an off-road vehicle for Mars, by including details about the simulation's dimensions, resource collection. The constraints of the problem are highlighted in green. It was important to include these as a reminder for the deadline and also limitations we must face during the simulation. We define attributes as the characteristics of our vehicle. However, to prevent limiting our possible solutions that we can come up with, we only included energy efficiency, as this was the only attribute explicitly stated that we needed to have. We didn't include things like durability, stability, or a modular shape because we didn't want our solutions to be constrained by them. Our team later identified further attributes to consider in our design process, which will be explored later. Finally, the last section pertains to the reasons why the previous attributes and objectives were included. This is done by relating them back to the context and problem itself, that is, creating a vehicle to help colonize Mars. It also reminds us of who the client might be, the space agencies. Overall, our team problem statement is a thorough guide to our future designs as it covers the necessary information of the problem without implying solutions, bias, or errors. This adheres to the standards set out in our engineering design textbook.
Using the understanding of the problem established in the problem definition phase, the concept generation stage enables engineers to clearly conceptualize design prospects that may contribute to potential solutions through the notion of design spaces. Design spaces, as called by Clive Dime, are spawned by an array of concept generation tools selected by the engineer, where the number of potential designs is intricately determined by the quantity of functions and alternatives required to satisfy the problem statement. It is evident that concept generation is essential as it fosters a bridge between theory and practicality by allowing for engineers to concisely map out their ideas in extensive detail, though what makes it truly imperative to the engineering design process is the byproduct of innovation. In reference to DIMES, Chapter 7 of Engineering Design, a project-based introduction handbook, the essence of design spaces is to convey a feel for the problem at hand, where an engineer's understanding of the problem can be enhanced by their understanding of the solution. Formal design tools, namely morphological charts, analog thinking, 635 method, and collaborative sketching, all focus on qualitative output to create design spaces with greater bounds. Mikhail Noble's Electrical and Computing Engineering Design Handbook underlines Thomas Edison's invention of the light bulb, where Edison understood that trying a large quantity of ideas was extremely important because failure is inevitable, emphasizing his lab tried and failed with thousands of different filaments.
The California Institute of Technology's study on factors that affect design outcomes correspondingly establishes, by broadening the initial pool of ideas, quantity yields quality as it leads to more creative design solutions. This sentiment can be elaborated upon by considering the results of combinatorics, where different design prospects can be grouped with each other to form a number of feasible solutions, as represented visually in a morphological chart. An example of the morphological chart can be seen below, which is our one for the Mars rover. Doing so elevates the potential of the design outcome by instigating a meticulous evaluation process for the designs that best satisfy the problem statement. Concept generation ensures effective communication between engineers and a time-efficient engineering design process. Concept generation design tools such as brainstorming and the 635 method would aid in the discussion of factors of functionality such as technical, operational, financial, and schedule viability, as it prevents obvious incompatibilities. It is crucial that this is the case, as collaboration of ideas from a diverse range of perspectives provides an insight into potential flaws with an individual perspective. The Georgia Institute of Technology's paper on the primary techniques of concept generation utilizes a case study of a successful startup design group at Graybridge, particularly noting when voices or ego become disruptive, the session's moderator would ask participants to work individually for 30 minutes. Seeing as concept generation ensures that engineers work both together and individually, it is vital to attaining healthy productivity.
Before we started concept generation, we had a quick discussion of important attributes that we wanted to meet in the rover. From this, we were able to rank these from what we thought was the most important requirement to least, and kept this in our mind through the next step. We decided that energy efficiency was the most important, followed closely by stability and carrying capacity. However, some of the topics are yet to be covered in the technical stream, so weren't considered in our concepts.
Seeing how concept generation is incredibly important in developing solutions to a problem, the team decided to use 3 methods of creating ideas: brainstorming combined with brainwriting, collaborative sketching, and a morph chart. Initially, we were allocated a certain amount of time by our team leader to generate 3 or more ideas, individually for possible rover designs. By doing this, we were able to avoid being influenced by the ideas of others and instead focused on generating as many ideas as possible. A few of these ideas can be shown on the screen. Then we contributed to each other's ideas and designs by writing questions, comments, and any additional thoughts, so that we could further develop these designs into something more plausible. The comments consisted of constructive criticism, which allowed us to enhance our more basic designs as a group. Upon group sharing, we found that many of these ideas were focused on practicality as opposed to creativity. As you can see, we explored different transportation methods, resource collection mechanisms, and rover shapes. Although there was minimal variation in features of the rover, we found that this method helped us identify common and practical yet uncreative solutions.
Our second technique of concept generation is the collaborative sketching, or the 635 method. Our team each created a base design before passing it on to the next team member for a greater range of ideas to be aligned. Here are some before the addition of the team's ideas and after the additions. See in design 1, 2, 3, 4. Closer looking to the design process of design 5, we can see one team member started with the body of the rover, and after passing it on to the next member, more modifications were added until a final design was accomplished. Having ideas brought to the paper from each team member ultimately minimizes design issues in the preliminary design process and brings clarity to collective design configurations. Our third and last concept generation is the morph charts. Each team member constructed a morph chart online, and in the end, we collated it together to create a team morph chart, which includes all of our team's members' solutions to each function. This method improves the team's creativity in generating design solutions, and organizing it as a morph chart further develops a more unique approach to each function, and thus a different solution.
To conclude, the planning and concept development stage is fundamental to creating the best design possible. Through the problem statement, we were able to express the main goal of this task and get all team members with the same understanding. This continues onto the concept development, where we were all able to provide our own ideas to solve the problem and then combine them to achieve an improved solution. Over the next couple of weeks, our team plans to further our design and keep on improving it until we find the closest to an optimal solution. A key part of this will be testing our design features to make sure that firstly, they are practical, and secondly, they are an efficient part for their role. Lastly, we will build the prototype and use it in a simulated Mars environment in week 10.